הנה. So, hi, I'm Erez from the Hebrew University, and first I'd really like to thank the organizers for inviting me here and giving me the opportunity to present the talk, because while my research is close to what people are interested in here, quantum simulation, it's not about superconducting qubits, so I tried to prepare some sort of an overview presentation which explains the field and the simulations of this particular kind of physical models that I'm going to introduce to you. And I'm trying to get less into details. So yeah, I'm going to tell you today about the quantum simulation of lattice gauge theories. We will also have to say what lattice gauge theories are. And I will focus on some special requirements that we have when we want to build or design a quantum simulator of such a theory, the challenges they impose, and some general methods for approaching them, which might be dealt with a variety of hardware platforms, as we'll see. So, and this is going to be based on some, if someone is really interested in the details, on the recent review paper that discusses pretty much all the things that I'm going to tell you today. I will speak about some newer results, but not a lot. So why is it interesting? Gauge theories are really a kind of physical models that we see in quite a lot of contexts in physics. First of all, in high energy physics, this is what the standard model provides us as a description for the fundamental interactions, for the forces that we have gauge fields, gauge bosons, which mediate the interactions among the matter particles. But also in condensed matter physics, we can see it in various different models as exact theories or effective or emergent theories. And we have things like the Torre code and string nets and quantum double models, Chern-Simon theories, several approaches to high TC, many things. So really, this mathematical structure of gauge theories is something you find in many physical areas. They are not only something that you find all around us, they are also very challenging. Why? In their core, as we will see, they have to do with local symmetries, which means that they have some separate symmetry transformation, separate invariance law associated with each point of space. That automatically means that our Hilbert space is highly constrained. One thing to deal with. Another thing is that gauge theories mostly involve highly non-perturbative physics, which has to do with things like running coupling and this sort of renormalization group features. And what it means in practice, for example, is if we look at quantum chromodynamics, the theory which models the strong interactions, the strong nuclear force, the one kind of matter particles, the quarks, we don't see them around us as free particles. They tend to bind together and form hadrons, like, for example, the proton or the neutron. And this is the effect called confinement, and it has to do with, with the very strong interaction, and basically, it's a very non-perturbative regime of the theory in which the forces are the interactions are very strong. So we can't use perturbation theory for that. And also one can relate it to some other interesting and exotic phases of such models that I will not enter here. So yes, these theories are hard to handle experimentally directly, because the forces are very strong. So if you think, for example, about an experiment in which you will pull out a quark from a bound state, you will have to invest pretty much an infinite amount of energy. So in a sense, the effect prevents you from studying it directly. So this might not be the way. Analytically, it's also hard to treat it, as we said, because we don't have perturbation theory here, okay? So we are in a non-perturbative regime where we don't have general prescriptions. We have to come up with something more suited to the problem. Then, very clever people in the early 70s, like Wilson or Kogut and Susskind, came up with the idea of formulating everything on a lattice in what's called lattice gauge theory or lattice field theory. And in this formulation, you can somehow perform some regularization of the theory on a lattice in a way that preserves the symmetry. And it turns out that this is also very useful for numerics using so-called Monte Carlo methods. So in this conventional approach to lattice gauge theories, what you do is you discretize both space and time. Okay, the lattice is also in the time direction. And then if you want to compute expectation values of operators or correlation functions, you do it as usual in quantum field theory with a path integral. You go to a Euclidean time, to an imaginary time, which gives you some Euclidean space, and the bottom line is that you can represent everything as some statistical calculations and use Monte Carlo integrations to find the values of your correlation functions. And this has been super useful and successful for many applications which are mostly static, such as the hadronic spectrum, the masses of the low-lying particles in the spectrum of such theories. But then there are problems in this formulation. What are the main two problems? First of all, when we go to imaginary time, we lose the ability to look directly at real time evolution, because the unitary time evolution operators become decay factors. They are very nice if you want to find the ground state, but it doesn't help you to evolve in time. So this is something that you lose when you use such a representation. Another thing is the famous sign problem, which is really some computational issue that you choose to represent fermions in a certain way when you deal with path integrals, with Grassmannian variables, and then when your chemical potential is finite in quite a lot of important scenarios, the probabilistic description that we need for Monte Carlo breaks down. I will not enter into it here, but it means that very important scenarios where you have highly dense fermions are not approachable with these methods. So new approaches are needed even within the framework of lattice gauge theory, and this is where quantum info and related fields have tried to contribute something new in the last decade or so. So one possibility is to do some quantum simulation, which is what I'm going to tell you about today, but also some things which are more digital, more quantum computing approach. And a lot of work has been done also by our group in terms of tensor network states, but this is not something that I'm going to enter. So, okay, quantum simulation is not something that I have to explain to this audience. Why is quantum simulation of lattice gauge theories useful, potentially at least? First of all, real-time evolution is not a problem. You prepare a state, you tune your parameters, you let it evolve in time. Either if you have an analog simulator, so you just let the system evolve, or you run some very carefully designed sequence of gates, but you get something which is time evolution or its equivalent. So time is real, and no problem with that a priori. Sign problem, again, as we said, it was an artifact of computing path integrals in a particular way. Here we don't do that. Fermions are fermions. Yes, we have to see how to control them and how to deal with them and how to measure them, but if we have a fermionic system in our experiment or something which represents a fermionic system, then we are free of this problem. So indeed, this is a field that has been going on for over a decade now, and even before that, if you look at works from the early 2000s, which actually realized some ingredients, some building blocks of such models theoretically and experimentally. Around 2011, 2012, there was really some nice peak, which you can say was sort of the beginning of this field, where several quantum info theory groups, mostly in Europe, started focusing on some proof of principle ideas. So now you can map gauge theories to atomic systems or other quantum hardware platforms. Until in 2016, the first experiment was actually done at Innsbruck, a collaboration of Rainer Blatt and Peter Zoller. And more or less from that point on, there was an explosion of the field. Many people started finding it interesting, not only from the quantum info community, also several experimentalists and some experiments were run. And today it's sort of a valid method accepted by high energy physicists, nuclear physicists, condensed matter physicists who are interested in such theories. So the field is growing, which is very, very nice. However, there's still a lot of work to do, because if at the beginning we were looking at conceptual issues of how to relate the world of gauge theories and the world of quantum hardware, today it's a question of how to make things feasible and bridge the potential gaps with the experiments, because the first experiments are great and all, but we would like to be able to design and work with the experimentalists on experiments that are more involved, that have to do with bigger systems, with more complicated symmetries. And this is what I'm going to focus on. So let me talk a bit about the system. So we present a lattice gauge theory in the Hamiltonian framework, which was introduced by Kogut and Susskind many years ago. In this formulation, unlike what I told you about the conventional approach, the lattice spans only on the spatial directions. So time is continuous. And then we have two kinds of particles, or two kinds of degrees of freedom in such models. We have the matter, which resides on the sides or the vertices of the lattice, and it's mostly fermionic, but doesn't have to be fermionic. And we have the gauge fields, which occupy the links of the lattice. And this is the first challenge that you meet even before we discuss the dynamics when you want to simulate such a model. The simulating platform needs to allow us to deal with both fermionic and non-fermionic degrees of freedom. Okay, two different kinds of statistics. And not every experimental platform allows us to do that. Now, this is a problem which can be easily dealt with if you have a single space dimension, because then you can use the Jordan-Wigner map and convert all your fermions to spins. But if you go above 1D, which is what I would say would be more interesting, this is not a solution, and you actually need to incorporate fermions and bosons or first quantized object into your simulating system. Then we have gauge transformations, which are probably the most essential ingredient of such theories. What are these? These are unitary operations which act on both the matter, red, and gauge field, blue, degrees of freedom on the lattice. They are local. That means that on each side I can choose and act with the different transformation, which I parameterize by the element of some group, and it acts on the matter side and all the links around it. And the state has to be invariant under all these transformations separately and independently. And this is why we say that the symmetry is local. Yeah, you can formulate it using a lot of group theory, but what I wanted to state here is that if we deal with a compact Lie group, which is what people usually care about in high energy physics, you can formulate the transformations in terms of their generators, and then the states have to be annihilated by the generators of the local transformations, which formulate some sort of a gauge of a Gauss law. Divergence of electric fields on the links minus the charge on the side. So the states somehow, these are the kind of constraints that our states must satisfy. On each side X, the Hamiltonian must commute with some set of generators. So that's a symmetry, but it's local because we have such an equation or such a set of equations for each and every X. Which brings us to the second challenge. We somehow have to impose and maintain, make sure that it's not spoiled, or somehow overcome, go around this gauge invariance, this local symmetry, because most of the simulation platforms that we have in mind don't offer this to us, let's say, naively or directly, and we have to deal with it somehow. That's the second challenge. And this also imposes some special structure of the Hilbert space and super selection, and these things were discussed before in Eran's talk. we have so many different symmetries associated with each lattice site, so it gives us, it really splits the Hilbert space into many super selection sectors, sectors of eigenstates of these constraints, which are disconnected by the dynamics. So this gives us sort of another challenge, which is strongly related to the previous one, so I didn't call it 3. The Hilbert space is really, really redundant, okay? This is what happens when you have a lot of constraints. And if we really care about one particular sector, which is what we do most of the time, simulating all the degrees of freedom is a huge waste of computational resources. So what can we do about that? And again, in one space dimension, it's simpler. Then you can solve Gauss's law and eliminate the electric field, and simpler. Now, what are the interactions that we have in Hamiltonians of such theories? These interactions that eventually we want to implement with the simulator, they must preserve the symmetry. So they must commute with the Gauss laws. They must satisfy all the constraints. One option, which is the interaction of the gauge field and the matter, is such a term in which we have a fermion that can hop from one site to the next. But of course, when a charge moves, it changes the Gauss law. It changes the charge on each side. So we need to somehow compensate it by changing the electric field on the site. And this is done by the presence of this U operator, which might have a very complicated definition, but qualitatively, this is what it does, okay? We have this U here. It's really a connector, something which mediates the change of charge here and charge there. So when the fermion hops, the electric field in the middle adjusts such that the Gauss laws are left intact. And this is quite a challenge to simulate, to implement on some simulating platform. Another important kind of interaction that we have is what is called the Plaquette interaction. Again, I won't get into it. It's something that becomes magnetic energy in a classical continuum limit. But it's a self-interaction of the gauge field with itself, okay? It involves all the links around each unit square of the lattice. Can be very complicated when the group becomes non-abelian and so on. And eventually what it means for us is that it's a complicated and very special and particular four-body interaction that we need to somehow implement, and most of the platforms will not just voluntarily give this to us. So this is what I call challenge 3. And of course, in 1D, we don't have to deal with it because geometrically there are no plaquettes. So I want to briefly tell you how we can handle these challenges in 2 different approaches. One is how we can directly try and implement all these things, and the other one is how we can go around them and play with them before the simulation. How we can change the model in a way that saves us some of the hassle. So when I want to deal with it directly, basically we can go to a few years back, and most of the proposals from the first days of this field they proposed to use cold atoms in optical lattices. Why? To satisfy the first requirement of having both fermions and bosons. So you can trap atoms in some laser-generated potentials, and you have atomic species which are fermions, atomic species which are bosons. You have to very carefully and cleverly design the lasers and the fields which create the trap such that everything will be trapped where you want it to be trapped. But in very, very general statement, I can say that we just create some very complicated lattice structure where fermionic atoms can only occupy the sites, because they represent the matter, and bosonic atoms, which represent the gauge field, occupy the links. How you associate each of the atomic levels with the different roles in the simulation and how you implement the interactions, that's a different story, and there are different proposals for that, and some experiments were done. But in general, this is a starting point for having something that includes both bosons and fermions. So then there are really several ways to deal with the second challenge of imposing gauge invariance, of having the local symmetry somehow incorporated into our simulator. The first way, which is very straightforward, but also a bit brute force, is just to force the symmetry, okay? We have some simulating system with some Hamiltonian that we have to fine-tune, but in a way that still doesn't preserve the gauge symmetry. But then we add to this Hamiltonian, using tools that we can use, terms which are proportional to the constraints, to be more specific, to the squares of the constraints. And we make them very, very strong, which makes some sort of an energy penalty in the spectrum. It means that it costs a lot of energy to leave sectors which satisfy the constraints, and then you can effectively derive some theory using perturbation theory which respects the symmetry. So you have to fine-tune the original Hamiltonian such that this perturbative expansion will give you the interactions that you want, but what's guaranteed for you is that the perturbative interaction will give you the symmetry that you want. So these were the works from the first days, and this was visited recently actually with some other methods that are simpler to implement this, using dissipation and using linear constraints instead of the quadratic ones that I briefly mentioned, and also using dynamical decoupling, which is something that we heard about quite a lot in this workshop. Another approach of analog quantum simulation, which is a less brute force, but requires a lot of fine-tuning, is to use symmetries that you already have in your simulating system and map them to the symmetries that you want to achieve in the simulator. What do I mean by that? We have these local constraints, this Gauss laws, this conservation of charges on sites. So if I still deal with atoms, I can think of what is the conserved quantity in the local interaction that I have in such a system. And these atoms are very cold. The only interaction that the only thing that they can do is collide. It's very cold, so it's S-wave collision. It's very simple to describe mathematically. And when two atoms collide like this, the hyperfine angular momentum is conserved. Of course, each such collision is a local process, so you can treat it as some sort of a local conservation law. So then, by properly choosing the different atomic levels which carry different hyperfine angular momentum values of all the atoms participating in this simulator and play the role of gauge fields and matter, you can make sure that you map the processes which are allowed by angular momentum conservation to those which are considered gauge invariant. And then you get the symmetry that you want. This is actually something that was studied a bit later by an experimental theoretical collaboration in Heidelberg. They played with this. This is a project we proposed. They played with some real atomic data and eventually realized some simple building block of that. And it works very, very nicely. This is actually something that can be done. So it's not an experiment of the entire lattice, but the building block of the most minimal building block was built. And this is very nice. Then we have to deal with the generation of the four-body interactions with the plaquettes. Now, the plaquettes, there are some methods to obtain them in analog, in the previous methods that I mentioned, but they rely on some effective perturbative expansions, so they will be very weak. I'm not even entering into it. A more clever approach to this would be to combine some stroboscopic or digital methods and use some trotterization and somehow tailor them effectively. So I want to demonstrate it with the simplest Plaquette term possible that you have in a Z2 gauge theory. You might be familiar with that from the Torre code, which is also a Z2 lattice gauge theory. So in such a theory, I have a spin. That's the degree of freedom, a single qubit on each link. And what I want to implement is the product of 4 sigma x operators, this Plaquette interaction. So what I can do, for example, is to put some control atom. I'm still talking about atoms, but it can also be, let's put some control qubit in the center of each plaquette. And then I need to act with a series of unitary gates, some controlled rotations which entangle it sequentially with each of the physical qubits on the links around it. And I can do it in a special way that will make sure that after I do this sequence of two-body operations, I act locally on the control, and this is exactly equivalent to the Plaquette interaction, to this complicated nonlinear term that I have on the 4 links. So this is a way to achieve the Plaquette interactions, and actually, at least from a theoretical point of view, you can generalize it to any gauge group that you want, using some trick called stators, which generalizes controlled rotations. And this is actually quite a common method today for implementing these Plaquette interactions that you can see in several proposals of the recent years. And recently, in a work that we did in our group, together with Alejandro González Tudela from Madrid, we took this algorithm and suggested how to implement it in a nanophotonic system or a cavity QED setup, where, since everything is inside the cavity, you can use the cavity modes and make sure that instead of speaking, letting the control speak with each of the physical qubits separately. So with atoms, we are just thinking about adiabatically moving the traps and taking the control to meet each and every atom. Here, you have the long-range interactions that the cavity gives you, and they can all interact with the controls can interact with the 4 links at once, which saves you some expensive simulation time, because you don't have to do it sequentially. And now I want to show you in a few minutes how you can go around these challenges, how you can actually, instead of dealing with them directly, what you can do, how you can simplify the model before you simulate it and you map it to some experimental platform. So I mentioned 3 main challenges here. Dealing with fermions, of course, on top of the bosons. If with fermions alone is a lesser problem. Dealing with the gauge constraints, and implementing the Plaquette interactions. So I'm proposing 2 different ways to overcome these problems, and each of them sort of deals or overcomes 2 of the things. One allows us to eliminate the matter using the gauge constraints, and if we eliminate the matter, we don't have to simulate fermions. The other one is to go to a dual formulation, which somehow simplifies the gauge, eliminates the gauge constraints and simplifies the Plaquette interaction. So what am I talking about?
What do you mean by eliminating the method? You don't want to simulate it?
I don't want to see, I'm going to talk about it in this slide. So what I mean is that I have this redundant Hilbert space, which includes both the fermions and the gauge field, and they are constrained. So I want to somehow solve this constraint or reduce it in a way that I don't have to simulate too many degrees of freedom. And I also don't have fermions in my model. So this, meets 2 of the challenges that we need to deal with. So here the story goes like that. Fermions in physical theories, they are subject to a global Z2 symmetry, right? This is what we call parity superselection. But if I make this symmetry, like any other symmetry, I can make it local. I can gauge it. And this is something that happens naturally if I already have a lattice. If I have the gauge fields to begin with, I work with a lattice gauge theory, and this Z2 is a normal subgroup of my gauge group. Then I have some local constraints which relate the parity of fermions on each side with the gauge fields on the links around it. And I can use these constraints to somehow write controlled unitaries which eliminate the matter. And I somehow transfer the statistics from the matter to the gauge field. So it's a long and tedious process. I will just briefly explain the idea. We can, yeah, even if I wouldn't want to do it briefly, I don't have the slides for that. So the idea is to somehow transform the gauge field operators using these local constraints in a way that introduces some auxiliary fermions that can fuse with the original fermions and leave us with hardcore bosons. The resulting model, which is what's relevant for us now, is a model in which instead of fermionic operators, I have spin raising and lowering operators, but obviously I can't just replace them by each other because the statistics is different. I decorate this Hamiltonian with these factors, which are operators that depend on the electric field values on neighboring links, okay? It means that I somehow make sure that the gauge fields take into account the anti-commutation relations, the statistics that the original fermionic matter imposed on my system. The bottom line is that I can replace the fermions by bosons, by hardcore bosons, and keep my system local, thanks to the presence of these local constraints. And the price I need to pay is to add these extra factors to my Hamiltonian, but they are all very local. It's not like Jordan-Wigner that you carry something from the beginning of the system or choose some preferred direction. So then you can move on and do it, and even in some cases you can actually use it to eliminate the matter completely, because once the matter becomes bosonic, you can use the constraints, the Gauss laws, and write controlled operations that simply eliminate it. And this is something that we studied recently. We took this general formulation and applied it to the simplest case with which we could demonstrate something, Z2 gauge theory, where we just have the Hilbert space of a single qubit on each link, a two-level system. And this is something that goes to more than 1D. This is the nice feature of this method. But in 1D, we could actually compare this method to other tools that are used that were used in the past for such quantum simulators, which I mentioned in the beginning, using Jordan-Wigner to replace the bosons by fermions, or solving the Gauss law to eliminate the electric field, which introduces some non-locality. And here, the bottom line is that we managed to actually build such an algorithm for such a quantum simulation that doesn't have to deal with the fermions directly and is free of the gauge constraints. So there is no redundancy. So if I look at the spectrum of the original theory, which includes all the super selection sectors, many states, which are just redundant degrees of freedom for me, at the end we just simulate something with a very small number of states, exactly the ones that satisfy the symmetry and the ones that we're interested in the simulation. And another thing that we can do, I think I will mention it in 10 seconds, is to go to a dual picture. A dual picture means, like we know from even from classical electromagnetism in the continue, you change from electric to magnetic variables and so on. So you can go and form and do the same trick also for lattice gauge theories and think about magnetic field variables and sort of vector potentials which produce the electric field. When you do it this way, you get rid, in 2 space dimensions, you get rid of all the local constraints. In 3 space dimensions, there is still some global constraint, which is much simpler. And you don't have 4-body interactions. Everything is just single-body terms or 2-body terms. That makes life very simple. And recently, we also showed, this is for pure gauge theories without matter. Recently, we also found a different dual formulation of abelian theories of U1 and Zn, which allows to do it also in the presence of matter. And that's another thing which can significantly simplify the simulation. Do I have another minute or not? Another minute. I have this slide. Thank you. So this entire idea, this entire concept of duality is also something very nice that one can use in quantum computing or quantum simulation, because this gave us the idea to think about dualities instead of mathematical transformations that you perform on your system, actually as physical actions, that you can somehow build a wider Hilbert space. If you have a theory that admits a duality transformation, a Hilbert space which includes both Hilbert spaces before and after the transformation, and we think about how you can physically take a state in one formulation, which is in a product of a trivial state in the other formulation, apply a set of unitaries and measurements, and convert it to the other side of the duality transformation. So we actually make the duality transformation a physical thing with local unitaries and measurements. This is a generalization of some methods that we used, for example, to create the plaquettes here, but it's something that can really be used in quantum simulation to allow us to convert in one experiment between two sides of a duality transformation. Different regimes of the model are easier to simulate in different sides of the transformation, and this suggests a way to actually, in the same experiment, perform this conversion physically. And with that I conclude. So what I wanted to show you today is that the quantum simulation of lattice gauge theories is subject to several challenges, different statistics, imposing gauge invariance, and complicated four-body interactions, and we discussed different ways which are direct and indirect for dealing with them. And yes, and I hope that I also managed to demonstrate that it's not only an exponentially growing field, it also has a lot of room for progress, for work, which is experimental, theoretical, anything you want. And I just like to thank my group for working on that with me, and for all of you for your attention. Thank you very much.